Hello everyone, welcome to the course on cryptography. In module 4, today we are going to discuss about RSA algorithm. So the pioneering paper by Diffie and Hellman, who introduced this new approach to cryptography and in effect challenged cryptologists to come up with a cryptographic algorithm which met the requirements for this public key systems. A number of algorithms have been proposed for public key cryptography. Some of these, though initially promising, turned out to be breakable. One of the first successful responses to the challenge was developed in 1977 by Ron Rivest, Adi Shamir, and Len Adelman at MIT, and first published in 1978. So the Rivest, Shamir, Adelman, whose name is introduced as RSA scheme, has since that time reigned supreme as the most widely accepted and implemented general purpose approach. This is implemented as general purpose approach to public key encryption. So this RSA scheme is a cipher. This RSA scheme is a cipher in which the plaintext and ciphertext are integers between 0 and n minus 1 for some n, and its size for n is 1024 bits, or it can be 309 decimal digits, that is n is less than 2 power 1024. Here we can examine that RSA has some with an explanation of this algorithm. So examining some of the computational and cryptanalytical implications can be seen in this topic, that is RSA. So under description of the algorithm, here RSA makes use of an expression with exponentials. Plaintext is encrypted in blocks, with each block having a binary value that is less than some number n. That is, the block size must be less than or equal to so this plaintext is encrypted in blocks, with each block having a binary value that is less than some number n. That is, block size must be less than or equal to log to the base 2 of n plus 1. In practice, the block size is I bits, where n lies between 2 power I to 2 power I plus 1. Here, encryption and decryption will be of the following form. For some plain text with the block M and ciphertext with the block C. So C can be written as, C indicates ciphertext here. Ciphertext can be denoted as M power E mod n. So M can be written as, M is a plain text. So similarly for decryption, we can write it as M is equal to C to the power D mod n. Here this can be written as M to the power of E into D mod n. Both sender and receiver must know the value of n. The sender knows the value of E, and only the receiver knows the value of D. Thus, in a public key encryption algorithm with the public key of PU can be written as E, n, and a private key of PR can be denoted as D, n. For this algorithm to be satisfactory for public key encryption, the following requirements must be met. It is possible to find the values of E, D and N such that M power ED mod N is equal to M for all M that is less than N. Second thing is, it is relatively easy to calculate M power E mod N and C power D mod N for all values of M that is less than N. And it is infeasible to determine D given E and N. For now, we focus on the first requirement and consider the other questions later. Now, we will see the relationship of the form m power ed mod n is equal to m. The preceding relationship holds if e and d are multiplicative inverse modulo pi of n, where pi of n is the Euler tangent function. We know that. So for p, q as prime numbers, then we can write it as p of pi in q is equal to p minus 1 into q minus 1. So the relationship between e and d can be expressed as ed mod pi of n is equal to 1. So this is equivalent to saying ed is congruent to 1 mod pi of n. So d is equal to e inverse of mod pi of n. Thus e and d are multiplicative inverses mod pi of n. So according to the rules of modular arithmetic, this is true only if d is relatively prime to pi of n. Equivalently, the GCD pi of n comma d is equal to 1. So this equation is satisfies the requirement for RSA. Now ready to state the RSA scheme. The ingredients are the following. That is, p, q are two prime numbers. So the private and the chosen. N is equal to pq. Public, the other one is calculated. E with GCD pi of n comma e is equal to 1, and this e lies between 1 and pi of n. D is congruent to e inverse mod pi of n. So the private key consists of d comma n and the public key consists of e comma n. Suppose that user A has published its public key and that user B wishes to send the message m to A, then B calculates C is equal to m power e mod n. So then B calculates C is equal to m power e mod n and transmits C. On receipt of this ciphertext, user A decrypts by calculating m is equal to c power d mod n. So summarizing this RSA algorithm, Alice, let us assume that Alice generates a public or private key pair where Bob encrypts using Alice's public key and Alice decrypts using her private key. So an example can be seen. So here as an example, some keys were generated as follows. Select two prime numbers, that is p is equal to 17 and q is equal to 11. Now calculate n is equal to pq. Pq is multiplying 17 into 11 will get the result as 187. So calculate pi of n for this. So it is 16 into 10, that gives 160. Now select e such that e is relatively prime to pi of n. So pi of n is 160 and this is should be less than pi of n. So let us choose e as 7, which is relatively prime to 160 and it is less than pi of n. Determine d such that de is congruent to 1. So if we multiply d value is e here e value is 7. We have to determine d such that d is congruent to 1 of mod 160. So d is less than 160. The correct value is d is equal to 23 because 23 into 7 is equal to 161 is equal to 1 into 160 plus 1. D can be calculated using the extended Euclid's algorithm. The resulting keys are public key pu is equal to 7, 187 and private key pr is 23, 187. So this example shows the use of these keys for a plain text input of m is equal to 88. For encryption, we need to calculate c is equal to 88 to the power 7 mod 187. Exploiting the properties of modular arithmetic, we can do this. So 88 to the power 7 mod 187. So this gives this value. that is 88 to the power 4 mod 187 into 88 square mod 187 into 88 to the power 1 mod 187 of mod 187. So if we calculate the mod of all these values, like first let us calculate the mod for 88 to the power 1 mod 187 gives 88. This is because 88 is divided by 187. We'll get the remainder as 88, and 88 square 187 will get the result as 77. 88 to the power 4 mod 187 gives the result as 132. 88 to the power 7 mod 187 gives the result as 11. Similarly, for decryption, we can calculate m is equal to 11 to the power 23 mod 187. So 11 to the power 23 mod 187 gives 11 to the power 1 mod 187. So calculating all the mods, and finally we'll get the result as 88. Now let us look at an example. This shows the use of RSA to process multiple blocks of data. In this simple example, the plain text is an alphanumeric string. Each plain text symbol is assigned a unique code of 2 decimal. Here we can see the key generation by Alice, like selecting PQ. P and Q both are prime numbers, but both are unequal. P is not equal to Q. Calculate n is equal to P into Q. Calculate pi of n is equal to P minus 1 into Q minus 1. Select integer e. GCD of pi of n comma e is equal to 1. E lies between 1 to pi of n. Calculate d. D is congruent to e power minus 1 mod of pi of n. Public key pu is equal to e comma n. Private key is d comma n. Encryption by Bob with Alice public key. Like plain text m should be less than n. Ciphertext c is equal to m to the power e mod n. Decryption by Alice with Alice public key gives ciphertext which is denoted as c. So we can get the plain text, that is m is equal to c power d mod n. So here we have a block diagram for RSA algorithm, which shows an example of RSA algorithm. So the 2 decimal digits, like for example, a can be is equal to 0, and a capital A as 26 to the power 6, like 26. A plain text block consists of 4 decimal digits or 2 alphanumeric characters. So this illustrates the sequence of events for the encryption of multiple blocks. Thank you.